So now let's move on to something more interesting, a quality search. We're looking for a particular record that has a match to a query of the form where column equals value. Now remember, we assumed up front that there would be exactly one match to this query, not 0 and not more than 1. And that's going to affect our analysis here, so keep an eye on that. We'll start with the heap file. In a heap file, we're going to scan from the left to the right, looking for the value that we're searching for. Remember, there's exactly one match, so at some point when we find that match, we can quit. In the worst case, we scan all the way to the end of the file. But in some cases, we might scan fewer pages and then find the record and quit early. So we have to think about what the probability is that we'll scan less than or more than, say, half the file. So the probability that a particular key is on page I is 1 over b. There's b pages. And the probability that the key is on any given page is 1 over b for that page. Now the number of pages that we touch, if the key is on page I, is I. So if the key is on page 1, we touch 1 page. If the key is on page 2, we touch 2 pages, and so on. And therefore, we can compute the expected number of pages touched in a fairly straightforward way. And we'll use this equation down at the bottom to do it. For a given page, we're going to take the probability that it's on that page, pi, and multiply it by the cost to get that page, which is ti. That's the number of pages we touch if it's on that page. And we'll simply sum that up, the probability times the cost, across all the pages, and that gives us the expected cost. So ti times pi, just substituting in, gives us I times 1 over b. And we're going to sum a quantity from 1 over b, from I equals 1 to b, and that's going to give us b times b plus 1 over 2b, right, which is approximately b over 2. And so on average, as we might expect, we're going to touch about half the pages in the file, right? In the average case, the item's about halfway through the file. So that should fit your intuition. Now let's look at the sorted file, which is a bit more interesting. What we're going to do in the sorted file is we're going to start on the middlemost block. If the object we're looking for is there, the tuple we're looking for is there, that's great. And if not, we'll go halfway to one end or the other looking for it some more. So it's binary search. And as we know from our algorithms class, the worst case cost for a binary search is log base 2, the number of things we look through, which in this case is b pages. Great. But what about the average case? We'd like to compute that as we did for the heap files. Is that also log base 2 of b? All right, well, let's sort of reason about this. What is the expected number of reads for different pages in a file? And this is a somewhat bigger file than we were looking at before with some color coding to help us. The middlemost page in this file, okay, we fetch it with 1 IO. What's the probability that our answer is on that page? Well, it's 1 over b, right? Now, whether we go left or we go right, we're going to go halfway to the end. Let's assume we go to the right. That's a page where it takes 2 IOs to find it, right? Because we did one search in the middle and now we're going halfway to the end. And the probability that we are 2 IOs into this file before we find something is 2 over b, because there's a page halfway to the right and there's a page halfway to the left, both of which are in teal. So there's 2 of those pages that have cost 2. Now, going from there, maybe we have to search deeper. We go halfway now to the right or halfway to the middle. Let's say it's to the right. That's a white page now. There was cost 3 to get to this white page. We went blue, teal, white. And there are 4 white pages like this in the file. So the probability that the answer is on one of the white pages is 4 over b. Okay. And going a little bit further, this was a path that took us 4 IOs, blue, teal, white, and then black. But there's 8 of these black pages. So the probability that the answer is on a black page is 8 over b. And if we want to sort of blow out these possible paths to the possible pages, we can think of this as a tree, a sort of search tree with levels. Level 1 pages cost 1 IO, level 2 pages cost 2 IOs, and so on. And this makes it pretty easy now to write down a closed formula for our expected cost. We have these log base 2b levels in this tree. For each level, the cost to get to that level is I. And the probability that our answer is at that level is 2 to the I minus 1 over b. Just looking at the examples of these paths up above, you should be able to convince yourself that's true. We can pull the 1 over b out of the summation here because it doesn't depend on I. And so that gives us the equation in the middle here. And then solving that equation on the right, we get log 2 of b minus some stuff, right, which is close to 1. So this is basically a log base 2 of b average cost as well, as we had thought. Okay, so filling that in the heap file, a quality search we said you go through about, on average, on expectation, half of the pages, so that's 0.5 B2. And for the sorted file, it's log base 2 of B times D. In both the cases, we multiply by D. That's the average time to read or write a disk block.